Okay, welcome everyone to the Astronomical Society of Edinburgh, wherever you are. This is what's happening tonight. So we have people in the hall here in Edinburgh. We have people, ASE members on Zoom, and we have hopefully people on YouTube as well. So welcome wherever you are in the world. Just a few slides from me before we get on to the main talk of the evening. That's what we've got coming up. Before we start, can we welcome our latest new member, Sayaza? I don't know if Sayaza's here. Nope, but can we applaud Sayaza? And to all the visitors as well. Our membership is back down to 156. It's the end of our membership cut-off year, so we've lost about 10, actually, which is not very much for what we normally do. So our membership is very healthy at the moment and growing quite strongly. So if you like joining us, then it's very, very cheap, only £30 or £15 for concessions. And if you join after the 1st of April, then you get an extra long membership until 2023. As always, you can stay in touch with us. Our website has everything on it, everything you want to know about society and what's coming up. We post regularly on Facebook and Twitter. And all our videos for the last few years, certainly over lockdown, are on our YouTube channel as well. And yes, you saw it here first, a showing of the new branding, well, not new branding, the new branded clothing and merchandise, which we'll be talking about in the next few weeks. So keep an eye open for that coming out. Quite a few things we might be doing there. Okay, these are the talks we've got lined up for the next few months. Next Wednesday on the 9th of March for members only, Imaging Observing Group, that is for members only, open to anyone who wants to join the society, obviously, and it's a really good, amazing place where we learn with each other about imaging and observing, and it's just a great place to talk about astronomy in general. This time we have a guest speaker who's Bruce Waddington, who has been involved in the PhD guiding program, which is what most of us use for our images. So that would be a really good way of finding out how to make it work properly and overcome all the problems that a lot of us seem to have. On the 18th of March, an online only talk will be about HF meteor trail reflections from Anchorage, Alaska. And that will be a talk from the USA, I believe. Yeah, but that's online only on Zoom for ASE members and YouTube for everyone else. Next month, the first Friday of the month, 1st of April, we're going to do something slightly different. We haven't done for a while, and this won't be on YouTube this time. It is for members only. So we'll be here and on Zoom for those who can't make it, but I'd urge people to come. It's going to be a bit different. We'll have some presentations from members, and we hope to have some of our antique instruments, right? Antique instruments here as well. So we've got a few old telescopes and transit tables and the like, and one or two things you might not have seen before as well. So we'll hopefully have those out. So please come to that. The next Imaging Observing Group in April, we're going to have a guest speaker, which is Des Loughney, who is a former president and still an ASE member. He's going to be telling us about eclipsing binary stars and how we can observe those and measure them as well. Another online talk on the 15th of April from Dr. Kate Lancaster, Astrolab Research Fusion. I'm not sure what the talk of that is, but that's generally what it's about. We'll provide more information about that next month. And 6th of May, it'll be a hybrid meeting again here and online. Weird New Worlds from Dr. Beth Biller, our Imaging Observing Group on the 11th of May. And then on the 20th of May, Emily Lagtawala about exploring Mars, 25 years of discoveries. So quite a lot of really good talks coming up. So keep joining us here in person or online. This is one of our outreach events that we run quite regularly, well, at least once a year. This will be the 4th one we've run. We've had 2 in person and 1 online. This is to help people who've maybe got a telescope sitting in a cupboard they've never used before or don't know how to use it, gathering dust, and they'd quite like to work out how to do it. It is now full for this one, so I'm afraid you can't come to this one, but there is a waiting list. So if you're interested in coming along, then join the waiting list. It's on the website and on Eventbrite. And as soon as we have enough people who are interested, we will run another one. They're really successful. People get a lot out of them, and yep, if you've got that telescope you want to start using, it's definitely the way to do it. And that's it from me. So over to our speaker tonight, Dr. Max Ruffert from Edinburgh University, and I'll pass it over to you.
Hello, can you hear me? Yes, okay, the loudspeaker seems to work. Right. Thank you very much. Thank you for the invitation to speak here and to tell you about a subject I like very much and I've been doing research on. My background is applied maths, theoretical astrophysics, so perhaps a bit distant from what I imagine most of you do, as in you have a telescope and you look at the sky. At least that's what I know from my friends. So I just wanted to tell you that many years ago, and we're talking like 4 decades ago when I was growing up, I did have a Newton reflector. I think it was 4 inches or 5 inches. And my parents indulged me, and whenever I went to the Alps or to Italy or so, we dragged it along and then I showed them things. And at the time, certainly there weren't any computers to do anything with the telescope, and even no motor. Okay, so it was all by hand. Anyway, so today I wanted to tell you about gamma ray bursts mainly, and then the various ingredients which go in will lead us to black holes and neutron stars, gravitational waves, neutrinos. As I say, it's mainly ingredients for everything, and I'll talk a bit about all those individual bits and pieces. And I hope there will be lots of time left over then at the end for questions. You're more than welcome to ask me many questions. Okay. So when I wrote this slide, which was, well, I updated it 4 or 5 weeks ago, it wasn't clear to me how it would resonate, how history sort of catches up a bit with us. So I wanted to start with the history of gamma ray bursts, and it goes all the way back to the USA and the Soviet Union, basically spying on each other, watching each other for atomic bomb explosions. Okay, there was to monitor the nuclear test ban treaty. So that was in the 50s. And the way they did that was to put satellites into orbit. And so the Vela satellite started in the 60s. And what these satellites would do was to monitor, to look for gamma ray flashes. Okay, so gamma rays are just like light, photons, but very high energy. So you go beyond ultraviolet and X-rays, and then you go all the way up to gamma rays. And so when there are these atomic bomb explosions, there are these gamma rays. So they put these satellites into space to look out for these gamma rays. Now, to detect gamma rays at the time, and well, things have changed a bit, but for many decades, that was the way to do it. You have a crystal which you put into space, and that crystal, when a gamma ray goes through it, will sort of light up and tell you, okay, we have a gamma ray came from somewhere. But it won't tell you from where it came. It will just tell you there was a flash, right? So the way to find where these gamma rays come from, you need several of these satellites or crystals, and then you detect arrival time differences, and from then you can sort of calibrate where it comes from. Okay. Now, then by 67, right, so whatever, 10 years later or so, things started looking a bit strange. Timings and positions. For one, the position so the satellites are in Earth orbit, they noticed that these flashes came not from Earth, right? So initially they started thinking, the Americans, are the Russians making atomic bomb explosions on the moon? And the other thing is that there were many of these flashes, much too many than atomic bomb explosions, which you could measure on Earth, conceivably make on Earth. Okay, so for a while it sort of sat there with the military, and then the first publications came out in 1973, and that's then when the astronomers started getting interested in these flashes, gamma ray flashes, which come from space. Okay. So now we jump 1-2 decades ahead in time, and I'll summarize the observations now as they are known more recently. So these gamma ray bursts, you can classify them into basically 2 types, which are abbreviated short and long. We have a few people who came in. I'll just direct you to many of the seats which are here. So when I refer to short bursts, they are bursts which are less than a second. Okay, they just go off, they flash a second, and that's it, they're gone. The long ones are between a second and a minute, perhaps a few minutes. So we're not, as astronomical events go, right, they're still very, very short. The next, or the other problem in a way initially was that these flashes come from what looked like random spots in the sky, from anywhere in the sky. So here you see a map of the sky. This is 2,700 bursts between 1990 and 2000. Projected on the sky as a map. Okay, so what you look at it, you stare at it for a while, and you don't notice anything, right? It just looks homogeneously flat. In particular, it doesn't look like you can spot the ecliptic, you can't spot the galactic plane, right? There's the moon, whatever, the sun, there's no concentration anywhere. So it comes from anywhere, right, in space. And it's like a second long or a minute long. So that was the fundamental problem. How do you catch these bursts in time? Because they flash and then they're gone. Okay, so that's why it took many decades for technology to catch up from those very first detections. Okay, so these flashes of gamma rays are very bright. Remember, we're talking the 60s, the 70s. As soon as you put a crystal into space to measure gamma rays, you measure them. Okay, they're not dim, they're not difficult to see. They are bright. That's in gamma rays. Okay, so you'll see various words like bolometric and naked eye. That's to remind me to tell you various things. So if our eyes could see gamma rays and so we're protected by the atmosphere from gamma rays, which is why you have to put these crystals out in space. So if we could see gamma rays, these flashes would be as bright as the bright planets. Okay, you would instantly see them if a flash goes off. Now, as you go down in energies to the other wavelengths, they get dimmer. So once we're down to what we can actually see by eye, the brightest flashes are just about visible, the magnitude 5, 6. Okay, so with a small telescope, if you happen to be looking at the right point in the sky at that right precise second, right, you would see them, you would see a flash. Okay, so they're bright. That's sort of the main takeaway point from this one. On the other hand, they're spread out over the sky. So now we know in more detail, but you could sort of guess it from the map. These flashes go off just distributed throughout the whole universe. They're not within our solar system. They're not within our galaxy. They're just distributed randomly, if you want, in the whole universe. And so because there is much more universe which is far away than close to us, right? Just by statistics, it means that most bursts happen far away. Okay, we're talking billions of light years, not millions of light years. Okay, so that's the distance. Okay. So now the problem, I think, is crystallizing in your head. On the one hand, right, there are these flashes which are so bright you can basically see them with the naked eye. On the other hand, they're happening at the far end of the universe. So what could it be? Okay, but that's not the only problem. So if you just look at during that 1 second, the brightness outshines the rest of the universe combined. You take all the planets, all the stars, all the galaxies, the energy just during that 1 second. Okay, so that's what we're talking about. And if you calculate back, it's something like 1/10 of a solar mass c². So you take a tenth of a solar mass matter, a tenth of a solar mass antimatter. You collide them, right? That will make a humongous explosion. That's what we're looking at in energy. Okay. But there is an additional problem. You remember the bursts are a second long, right? Or they have spikes that are a tenth of a second long. They're short, right? So how do you produce all this energy in that short time? That's the basic problem. I'm a theoretical astrophysicist. I have my models, I have my computers. I can merely take the sun, slice it in half, slam the two halves together. That will make a big explosion, right? The problem is it takes half an hour, that explosion. It's not a second or a tenth of a second. So that combination, in a way, is the problem. How do you get out all this energy in this short time? And so if you just calculate back, right, how small an object, so the problem of the sun is too big if you do that, okay? So how small an object do you need in order to make these short bursts? And that's where you end up with neutron stars and black holes. Just from the size, we're talking 10 kilometers, 100 kilometers, objects of that size, geometric size, but they need to have a solar mass or close to a solar mass in mass. Okay, so now you see how I hope the story is slowly coming together. Right, so now we have a sketch for, now comes the sort of the theory, the theoretical astrophysics. What models are there, or what ideas do we have, what these gamma ray bursts could be? Okay, so ignore for now this scenario down here, the bottom left one. I'll just have a look at the other three. So basically, you just take this, they're called compact objects, right? A neutron star and a black hole, and you collide them, you smash them together in some way, okay? There isn't much difference if you take two neutron stars. We know they exist, binary pulsars, eventually they merge. So they will do it, or if you have a binary of a black hole and a neutron star, same thing happens, that eventually they will merge, and then something will happen. And the idea which you should have in your head for all the gamma ray bursts is the following. It's this sketch in the middle, is that you have a central black hole which accretes matter from a disk and then spews out a jet. And if that jet happens to be pointing towards us, that's when we see the burst. Okay, so every time a burst goes off, that indicates, right, that you have this cataclysmic collision or something happening where you're forming a black hole and a jet is pointing towards us. Right, so you take away. Every burst means a black hole is born. That's already good. But we don't even see them all, right? Because that jet has to be pointing towards us. There are many more which are pointing in other directions and we don't even see them, right? Okay. The bottom right scenario is a slight variation on it. That's where you start with a huge star, a 50 solar mass, 100 solar mass stars, or something very big, which then collapses. So you might be aware these big stars, they collapse and make a supernova. But in order to make a supernova at the center, you need a neutron star in order for this shock to propagate out, but that's a different story. Failed supernovas, where you get a black hole, are the ones which will produce gamma ray bursts if they are also rotating, because in the end, you'll end up with a disk around a black hole being fed by the star, and then you get this jet, and if it points towards us, you get a gamma ray burst, okay? And if you look at the time scales, the merging time scales of binary neutron star or a neutron star of a black hole, those are short enough, we're talking seconds, to produce the short bursts. And these big stars, because they can feed the disk for a while, those will naturally produce the longer bursts. So these two different kinds of bursts which we observe have a mirroring in the different models which we have in our heads. Okay, so neutron stars, we know they're observed, they're 1.4 solar masses about, or 15 kilometers, a bit about the size of Edinburgh or so. And then black holes, those tend to be more massive. Well, we can come back. So I wrote down typically 5 to 10 solar masses, but those are the stellar mass black holes. They'll be slightly smaller, 10 kilometers, the horizon radius for the sun, that's one solar mass, that's 3 kilometers, but it's more or less of the same order, which is why we get our short bursts. Right. So with that in mind, that's where now applied mathematicians and theoretical astrophysicists come in. We want to simulate these models, right? So I'll skip that part. If you look very closely at my slides, at the top, you will see roughly where we are progressing. And right at the end, I won't go into doing any of that. Those are the details. If you really want to know details about the maths, about the physics or stuff, I've hidden it at the end. But I think time will run out before we get there. Okay. So what should we have in mind? So now I'll show you each of these buttons as a video. I won't show them all, but I'll show you a few calculations. So these are actual simulations of what we think goes on. So I'll have to apologize, these windows, couldn't get rid of them. Right. There we go. Is this, can we dim the lights perhaps a bit for this one? So I'll just repeat it as we go, and I'll explain the bits which you see. So the gray sphere, the big one, that's supposed to be the black hole. The colored surfaces which you see going around, those are densities of the neutron star. And what you will see is the neutron star being shredded to bits, and every now and then I zoom in and out. You see a sort of a box in the background. That's just to give you a bit of orientation. And you see a clock on the left-hand side. So when you see the fast pointer that goes around, the fastest one, when that goes around once, that's 1 millisecond. Okay, so we're really talking very short time scales for the merger itself. Okay, so let me just restart the whole thing from the beginning and just explain again. So you have the black hole at one side and the neutron star. So the different colors which you can make out show you different densities. There's like a gray bit in the middle, which is the highest densities, and then you go out with lower densities. And as the neutron star moves around the black hole, the two objects will merge, so they get closer and closer. And if you're wondering why, that's due to gravitational waves, which I will come back to. And so as the objects get closer, bits of the neutron star get absorbed by the black hole. And then it's called tidal effects. The neutron star gets sort of pulled, shredded apart. Now I zoomed out a bit, perhaps I should stop. So you can see this big, well, you can just about see the big arc. That's material being flung out of the system. And then closer to the black hole, it's difficult to see, the neutron star is trying to reform itself again under its own gravity as it goes around. Sort of manages, but the next time around it comes so close it gets shredded completely. Okay. And then at the end we get a disk forming around the black hole. So as promised, right, so we get this disk with material. The material falls into the black hole, and then you get a jet, which we don't see yet at these early stages, which will go perpendicularly to the disk, up and down, basically, in our point of view here. And the disk now remains for quite a while, right? So this whole thing takes a few milliseconds, but the disk will stay for tens and hundreds of milliseconds. Okay. The other videos, so that's the main concept which you should have in mind for these merging neutron stars. The other videos are basically variations of it, because so these are numerical simulations. There are lots of parameters I can play around with and I can change. So the next one is a more realistic equation of state. So equation of state is just a fancy name for how do I describe the neutron star material. So you will notice that the neutron star colors, the neutron star looks all a bit rougher. That's just because there are many more physical effects included in there. And the other thing you might notice is that I started with a smaller black hole, a less massive black hole as well. But more or less the same thing happens as the neutron star. As they get close, the two objects, the neutron star goes around, gets torn apart, shredded, and then forms a disk around the black hole. Okay, so these videos which I'm showing you, they only show you the density. Okay, now there are many, many steps between what you see as the video, which output of my calculations, and what you can actually see by telescope or with these satellites that I told you about. Okay, let's go on. See a different calculation. So in this case, I gave the black hole a spin, so it's now particularly small and tight. And if you look closely, you'll even see it grow as it absorbs material and then as it slows down. But more or less the same thing happens, okay, as we go along. Okay, now, this material is incredibly dense. I mean, we're talking the density of the nuclei of atoms. Okay, I don't think I need to put any numbers to it, but it's certainly many, many millions and billion times more dense than anything you find normally around here. Okay, it's certainly also much, much denser than the sun, for example, which means although this material is ultra hot and ultra dense, all the light, what we would see, is stuck in there. I remind you, you probably are aware of it, the sun, for light to get out from the center of the sun takes 1 million years, and that's our sun, and average density 1 or 5 or 10, right? This is, as I say, billions and billions. So there's no way to get out photons, anything observable with photons out of it. So that's where the neutrinos come in. Those are elementary particles. I'll come back to them in a second as well. So as the calculation goes along, I can calculate how many neutrinos are emitted out of this. So now I need to, let's see, re-explain again a bit. It's more or less the same setup. You see slightly lower resolution, only you'll see several differences. So the black hole now is properly black, okay? The neutron star is transparent. That's because, and I'll come back to it, neutrinos hardly interact with anything. So although neutron stars are as dense as nuclear material, it's still optically thin, so neutrinos can just pass through, which is why you don't see much of it. Okay, so in order to see something, I put some stars in the black background, okay? So you see a shadow going over these stars, okay? So then as the calculation proceeds, the neutron star heats up, and that's when it starts emitting neutrinos. So now the brightness and the color shows you neutrinos. It's if our eyes were sensitive to neutrino light, what we would see. The neutron star heats up and then gets shredded. As it gets shredded, the densities go down again, so it gets transparent again. But then as it heats up, the disk starts becoming visible. It is there. You've seen the densities, right, in the other videos. And so it starts emitting in neutrino light. Okay. And again, I can show you perhaps, yes, just skip these. Different variations. So here now I have 2 neutron stars rather than a neutron star and a black hole. In a way, the same thing happens. Okay, this is just to show you there's not much difference. It's just the 2 neutron stars have slightly different masses. And you can see how the lighter neutron star gets shredded by the heavier neutron star. So, but you remember, in order to make a gamma ray burst, we need a black hole accreting from a disk in order to make our jet. So here now at the center, the 2 neutron stars have to form the black hole first. Okay, so the gamma ray burst will be less energetic because a lot of material has to go into forming the black hole rather than making a disk and making a jet. Okay, and then the disk in neutrinos, let's have another look there, basically just sits there for a while, as I say, 100 milliseconds, a second or so, and just continues emitting neutrino with this black hole at the center. Okay. All right. So Me personally, that's what I've been calculating, these neutron star black hole mergers. But you remember there was this other model of you have a failed supernova collapsar producing gamma ray burst as well. So here I'll just show you some old NASA, and so those are animations, not calculations of, yeah, let's take that one. What happens there? So let's see. So there you see, right, the whole star, and we're zooming into the center. The star is rotating. You form the black hole, it's sort of collapsing, and then you get this disk and the jet in the star. So this jet has to first, you know, drill its way through the whole, all these layers of the star, and then as it comes out, once it points at us, that will be our gamma ray burst. Okay, so those are the long ones, long gamma ray bursts. Okay, right. I think this is more or less the same thing. Yes, and so they're longer because, as I say, you have more material, right, in the star, which can fall onto the disk in order to, you know, feed the black hole to make this jet. And that's, I guess that's all there is to it. There's not much to it. Okay. Okay, so now I come to these ingredients. Okay, so black holes, gravitational waves, and neutrinos that go into the models for the gamma ray bursts. So the first one, question: do black holes exist? And I put it up because until about 2016, it was really only indirect evidence. I don't know if everyone is sort of aware of it. We've all got used to black holes, right? You see them in science fictions and films and wherever, and everyone was convinced they exist. But it was only indirect. And sort of I'll explain that a bit in a second. It's just the mismatch between the black hole being black and we having telescopes wanting to see light, right? So, okay. You say, well, okay, now we are further because, well, there is the first ever picture here of the black hole in April 2019. So that must have nailed down the case. Nearly, okay? So this is a supermassive black hole, I should just say, the center of M87 at 16 megaparsec. But the thing is, so what? This is a disk around a black hole. I'm not contradicting that. It's just you need to be aware that the black hole is not this dark spot which you see at the center. It's much smaller than that. Okay, I mean, it's right. So this black spot you see at the center is a shadow in a way of the black hole, and so the whole picture you should be looking at it like rotated by 90 degrees, because the brightness is not indicating that it's near, but it's indicating that it's coming towards us very quickly. So if you imagine a disk going around, the bits which come towards us very quickly will be on the one side rather than at the front, which is why you should be looking at it rotated. Okay, so that's, I mean, okay, let's say 80–90%, we're nearly there with existence of black holes. The thing is, it was the gravitational wave detections which finally nailed down the existence of the black holes. And somehow I felt, and that was in 2016, right, well, when they got measured and then publicized, it somehow went lost, I think, in the news when these gravitational waves were mentioned, were detected. That is a big breakthrough technologically. But what they always said, oh, Einstein is right, and then gravitational waves exist, and went along that line. It wasn't emphasized that those measurements of the gravitational waves were only possible due to black holes. That was our direct one-to-one relationship. Gravitational waves are bent space-time. Black holes are bent space-time. There is, you know, there's a one-to-one relation between it. And I thought that went a bit lost in the whole thing. So that's why I'm making a bit of a point here. A nice feature of the merging neutron stars and black holes gravitational waves. You know this time scale which I was mentioning, 1 millisecond, 10 milliseconds. if you make waves out of it, that's exactly 100 hertz, 1000 hertz. That's what we can hear, right? So the best cases of these gravitational waves, you can just listen to them. So that's what I have here, and I hope the technology will now work. Took a bit of setting up. So the first one is natural. So that's one-to-one, what we hear. So you have this plop, plop. Okay. And then the next one is just increased a bit. So you hear how it increases the pitch. Okay, but that's a factor of 10 or something. It's not much. It's completely natural to what we can hear. Let me just repeat it again. And I'll be quiet. Okay, so what are you actually hearing with these waves? I need to explain that a bit, but it's completely, get back to it in a second. Okay. So you have these two objects, black hole and neutron star, right? They're orbiting each other, and every orbit makes like a bump in the wave. Okay. As they get close, they spin faster and faster. That's the pitch going up. And then at some point they crash together and then it stops, right? But as they go in, they go faster and faster, and that's the pitch going up. So in my models, I can calculate the gravitational waves, which is indicated on this plot. So you can see like the thin line, right, speeding up, going faster and faster. And then eventually it stops at some point because those 2 point masses have then crashed into each other. Once they're extended, black holes, neutron stars, right, they're small but not zero, they do the same thing initially. They come close, speed up, you hear the pitch go up, and then they merge into each other. That's now this more solid bit. And at the end, this object that forms either a black hole or a very massive neutron star will wobble around for a while, still producing a few gravitational waves, but the loudness is very much reduced. Okay, and that's when it cuts off then. But otherwise, the gravitational waves, so I don't know if, again, if you involve Einstein and general relativity, and so you might sort of feel a bit reluctant to think too closely about it, but that is really nothing complicated. And again, so now my move sun example. So let me just start perhaps something which you know. So the time it takes for light to reach us from the sun, 8.5 minutes, right? That's how far away the sun is. Okay, so if I don't know, I could switch off the sun, or I just make it dark somehow, we wouldn't notice, right? For 8.5 minutes, that's how long it would take. Okay. Now we know the sun has a magnetic field as well. So what happens if I do the same? I just wobble around the sun's magnetic field. We have magnetic fields detectors on Earth or in satellites. How long would it take for us to know? I mean, would it be instant because it's a magnetic field? Or how long would we have to wait until we notice that something is changing with the magnetic field of the sun? Think about it for a second or two. I hope you come up with the answer. It will be the same 8.5 minutes. Okay. Why? Well, it's not coincidence. I mean, okay, you can say magnetic fields are related to light, but it is because the speed of light is the maximum speed. Okay, so the light waves go as fast as they can, which is the speed of light. That's how we called it. The same with magnetic fields. They will propagate as fast as they can, which is the speed of light. Okay, so as we are going around the sun, right, the sun is at the center, the Earth moves around the sun. So what happens if I move the sun by a bit? How long will we just go around the sun as if it were where it was, right? Or would we notice instantly that the sun has moved? How long would it be? Sort of trick question. It's the same answer, 8.5 minutes, right? So and what links us to the sun is gravity. So as I move the sun, right, this gravity wave takes 8.5 minutes to reach us, and that's it. That's basically the gravitational waves that we're talking about. There's nothing more complicated to it. Okay. This is what one of the best measurements looks like from the gravitational wave detectors, and it is you measure the wave, right? You actually measure the wave, and I'll come back to that again. I'm not sort of emphasizing always waves. We're talking about waves, which is different from what you see in your telescope, right? You collect energy with your mirror. You don't measure the wave of the light. Okay, I'll just go back to the statistics of what these gravitational wave detectors have detected. So all the blue dots are black holes, and the way the figure works is that you have two blue dots connected by a line, a vertical line, and then you have an arrow going to another blue dot. And that just indicates the bottom two black holes merge to the third one above them. Okay. And so you can read off the masses. Can you? If not, I'll just read that. So 1 is down at the bottom, 200 is at the top. Okay, so most of the black holes there that we're talking about are about 50 solar masses, 20 solar masses. That was a surprise in itself. So most of the measured objects are black holes. The orange dots, those are the neutron stars. So there are a few cases where mergers of neutron stars have been measured by gravitational waves, and they then produce a black hole. Okay. The red dots and the yellow dots at the bottom, so the red dots are the black holes and the yellow dots are neutron stars, electromagnetic, so seen with light in a way, or pulsars or something. So that's the classic, the range of the question, do black holes exist? Well, those are the ones we thought are conceivably black holes indirectly. And the same for the neutron star masses, you can see they're more or less all similar 1.5 solar masses. Okay, and the first neutron star merger measured by gravitational waves also went through the media because that was a confirmation of all our gamma ray burst models, right? Which was around for, as I told you, decades. Okay, so that's that. Right, quick mention about neutrinos. So neutrinos are particles, sometimes called ghostly particles, elementary particles, because they hardly interact with anything. But again, I want to take away any fear you might have, any bad ideas you might have about neutrinos. They are particles, right? With properties of particles. They might be tiny in size, they might have a tiny mass, they might only interact very little with anything, but they're particles. When I say very little with anything, I've heard, just remind you, it takes a light year of lead to stop the neutrinos. Okay, you remember X-rays, when you have images, you go under X-rays, the doctor will have some amount of lead on him, right, to stop the X-rays. Neutrinos, you need distinctly more. Okay, so that's what I mean with they interact very, very little, and why sometimes they're referred to as ghostly elementary particles, but they're particles. Okay, and where do they come in all our gamma ray burst story? So that was, you remember, all that is thick, optically thick. You can't get light out of it. Okay, but that's what we see with our telescopes. Okay, now the neutrinos, the only interaction they have is, it's unfortunate, it's a bland name. It's called the weak nuclear force. Okay, but it's a force just like gravity or magnetic fields, if you want. Okay, so just as not everything is magnetic, if you have a bar magnet, right, you can go and trying this is magnetic, this is magnetic. Some things are magnetic, some things are not magnetic. The same thing happens with neutrinos. They only will interact with things which via this weak force. And so you need some intermediary between the neutrinos and light. Light as an electromagnetic wave, it connects to electric and magnetic fields and charges. Okay, so you need a particle with a charge. And one of the lightest ones is an electron, has both charge and will interact via the weak nuclear force. So that's what I try to indicate in my sketch there, in my calculations. When the two neutron stars merge, I calculate how many neutrinos come out. I calculate the annihilation of neutrinos and antineutrinos, which produce electrons and positrons, and those then produce the gamma rays, right, which we see as gamma ray burst. Okay, so that's where the neutrinos come in. And on the whole, the time scales and the energies more or less work out. Another way of getting out energy would be via magnetic fields directly, sort of, but those would also couple to the photons, which we could see. That's work in progress. Okay. Now, last 2-3 minutes, I want to speak about the detectors. Okay, and then we come back. So first gravitational waves and then neutrinos. But these detectors, they look very different from telescopes, and there is a good reason for it. So the gravitational waves, detecting those, you should have as concept in your mind listening, not looking. Okay, I've tried to drive it home by making you listen to it, but you have the same sort of problems as in when you listen to something. If you just block one ear and you just listen with the other ear, it's difficult to pinpoint where does it come from. You need two ears, right? The same thing is with gravitational wave detectors. Each individual detector will tell you there is a wave coming from somewhere, but you need several of them in order to pinpoint more precisely where the waves are coming from. So there are two big ones. And the way you measure gravitational waves is you just try and measure distances very precisely. And so the longer a detector you have, the more precise you can measure. So in the USA, there are two of them, each 4 kilometers long, these arm lengths. By Pisa, there is one called Virgo, it has 3 kilometers, and then there is one in Japan, also 3 kilometers, which is underground, called Kagra. Okay. And I also emphasize that you measure the wave form, not the energy. You're not collecting light like with your telescopes. Okay. And that's important because it's a mathematics. You know the 1/r square law. You might have heard it via other things, right? Applies to your telescope, but it doesn't apply to the gravitational waves. Those go with 1/r. Now, that might be mathematics. What does it actually mean? If you think back to the development of the telescopes, you started with Galileo, and then they got bigger and bigger and bigger. And basically, we worked our way out. He looked at the moon, and then the moons of Jupiter, and then the next star. And eventually, right, the telescopes got bigger and bigger, and we worked our way to the end of the universe. That's because of the 1/r square law, right? As you go out, the 1/r squared dilutes your energy very quickly. Whereas with the gravitational wave detectors, it only goes down with 1/r as you go out, right? So initially, it's very difficult to measure gravitational waves, which is why you need these big detectors. But once you have one, right, you're basically half the way across the universe. There isn't much further to go because you detect more or less everything that's happening, nearly everywhere. We're not there yet, but nearly. Okay, so in that sense, it's more like listening, right? It's not like collecting light like your telescope. Okay, the neutrinos, this will be my last slide now, they nearly interact with nothing, right? So how do we detect them? Well, we need a lot of something for them to interact with. There's no way around it, okay? So in Japan, they built a 50,000-ton water tank. What you can see there is a dinghy with 2 people in it, okay, swimming on the water once they drained it to clean it up or so. And each of these dots, which you see, is a photo multiplier about 0.5 meter in size. And so what happens is that the neutrinos would go in the water and then collide with an electron, and the electron emits a light wave, and then you can see the light. Okay, but you need a lot of water to do it. the other two, right, go a step even further. So there is ice cube. It's the cube we're talking about is 1 kilometer side length, a cubic kilometer of ice, which is about 2 kilometers underground. And there you have the Eiffel Tower for size. And that dot, that one there. And similarly, in the Mediterranean, there is, it's called Antares, 0.3 kilometer cube of water, which they're just measuring, same as Japan, again with photomultiplier tubes there. The last sort of, by the wayside, Super Kamiokande, you see the Ka in Kamiokande, it's the same Ka as in Kagra, because it's the same mountain, the Kamioka mountain in Japan, where they're just doing these experiments. Brilliant, thank you very much. That's it, that's me done.
Thank you very much for that. It's fantastic.
Thank you.
What I find hard to get my head around seeing those simulations is the speed at which these huge bodies are rotating around each other as well. It's just milliseconds. It's just staggering.
And the energies involved are humongous, which is so. Can I just go back just to point? So you remember how I told you it takes a light year of lead to stop the neutrinos? In the simulations, I just quickly went over this where I said, oh, neutrinos interact with antineutrinos and annihilate. That's how dense they are, the neutrinos. They are so dense that they interact not even with matter, but with each other.
Okay, any questions from the hall, first of all?
Thank you very much for an excellent talk.
Thank you.
I'm just curious about the jets.
Yes.
How are they produced?
So by magnetic fields. So it's an excellent question. So since I haven't done the calculation myself yet, I didn't show it, but there are calculations. And so with the material that falls into the black hole, there is a bit of there are a bit of magnetic fields. Okay, and as you fall in, these magnetic fields get stronger and they get wound up. Right, so the material falls in, winds up the magnetic fields. Some of the magnetic field will fall into the black hole, but some of it will just wind up and then direct the material. So winding magnetic fields on its own, okay, you have a magnetic field, but then the other material that flows in is then directed along the magnetic fields and produces this jet. Yes, that's an excellent question, yes.
Fascinating thought. Thank you very much.
Thank you, yes.
Is that better? Yeah. Good. You talked about that we only see those jets that come towards us, or those gamma rays that come towards us.
Yes.
So what percentage? I'm just saying an estimate.
A few percent. So it obviously depends how wide this jet is, right? And that is linked to how, well, that's not super, how very relativistic, how fast it is. And it is about a few percent. So there's a factor of 50, 20, 100, somewhere in there of burst, which we don't see as gamma ray bursts, but which we do measure, will measure as mergers via gravitational waves. The very first one being it. Okay, but obviously the statistics is in that favor. So this very first neutron star LIGO measurement 2017, which is in there somewhere, is exactly one of this kind, as in it's clearly a merging neutron stars. Everything works nicely, but the flash which we see is very dim. Okay, because the jet doesn't point towards us. Everything else, all the other bits which I mentioned, what fits nicely is, so this material, as I say, is nuclear material, and as it falls in, the material is reprocessed and then gets jetted out again. Okay, and so the material which comes out is a mixture of nuclear elements, and each one of them will have nice lines which we can measure. And the first calculations when they were done indicated, so there's a technical part which I skip, but a lot of gold is produced, and that went through the media, as you can imagine. And so independently now of the gold, the mixture of nuclear material which we calculate, it matches what we see from the lines, from the absorption lines and emission lines. But it wasn't a bright burst. No, exactly for that reason. Yeah.
Are there any other questions at all?
Thank you. Thank you very much. If the gamma ray bursts are directed towards us by the jets, how would the gamma ray bursts detected from the initial atomic explosions, how would they be transmitted? I thought they were like significantly less energy.
Oh, but they're significantly closer.
Right.
Right, they're in Russia or in the Pacific. In a way, it's the other way around. You can see how bright these cosmological bursts are, that we see them so readily as soon as you put a crystal into space. But basically, yes, I mean, the military did the calculation, how much gamma ray burst comes out of a normal nuclear explosion, what size crystal do we need, and then you can measure them as you go around the Earth. And that's in addition to everything else. I mean, obviously, every explosion also makes earthquakes, and you can measure those, and so yeah.
Thank you, and can I thank you as well for that talk? It was excellent. But how are we able to estimate the distance to a gamma ray burst?
That's an excellent question, which I underlined because it took 2 or 3 decades to answer it. So a flash goes off somewhere in the sky. So first you need, automatic robotic telescopes to catch it in time with all our telescopes. So the gamma ray itself doesn't have much information about the distance. Okay, so the crystals itself can't tell us much. However, we know, right, we have a lot of telescopes and detectors and whatever, as long as we could point a telescope in the right direction and catch it, we could see, is it linked to a galaxy, for example, or we can look at the absorption lines, right, for with distance. So that was a big step, right? So once we had all this, I mean, it was basically an automatic setup. The burst went off, the crystal in a satellite pinged, automatically it went to some telescope, even robotic ones, which then automatically caught it, right, within a few seconds. So the optical light is a few minutes. So it's the gamma rays, which are seconds, and then as you go longer in wavelength, you go longer in time as well. So once that hurdle was taken, then we could judge the distances. The first indicators were the picture I showed, right? So once you got a map where you couldn't see, right, there's no galaxy, no ecliptic, no nothing, that already somehow told us, right, it must either be very far away, right? Or perhaps in our solar system, enveloping the sun or something. But yes, so once we got to this stage, so beginning of 2000s, then we had an idea they were far away. We didn't know how far, and that's now all become clear. But yes, that was the first big stumbling block, because linked to the distance is the energy, right? I mean, as long as they were close, you didn't have any energy problem.
Okay, we have one more question here, then we'll go into the Zoom questions.
Thank you, Max, for a fascinating talk.
Thank you.
We're all familiar with the dangers posed by solar flares to life on Earth and so on. Are there any dangers that we are aware of gamma ray bursts, or are they too far away?
So yes, so I told you these bursts thankfully happen far away. Okay, I don't think a burst has happened in our galaxy that was pointing at us. Okay, so if you, so it's an easy calculation, right? There is, so it's typically a burst a day that we see as soon as you put a crystal into space, right? Times 100. So that's how many bursts there are in the universe. You divide by the number of galaxies in the universe, you know how often it happens in a galaxy, right? It's easy enough. I'm a theoretical astrophysicist, right? The number is a few 100 million years. So once that was written down, you can find a few papers who connected with the extinction of the dinosaurs. That's a few 100 million years, okay? Indeed, if a burst and close by burst would have the jet towards us, that side of the Earth would just be fried, evaporated off.
Are you okay for a few more questions?
Certainly, certainly,
We'll
yes.
pass over to Zoom then. So.
Hello, Sarah. Can you hear us and can you coordinate?
Yes, I can hear. So we have a few questions. The first is from John Murrell, who asks, are gamma ray bursts related to fast radio bursts?
I need to think about that. So that's fairly modern, I must admit. So I guess the answer is no, but it depends on how you define related, right? So they're certainly not related in this sense. In the sense of you take two neutron stars, a neutron star and a black hole, and you collide them and they merge, because that only happens once. It doesn't happen again to that particular neutron star black hole. And as far as I recall for the fast gamma, for the fast bursts, they repeat. Okay, so it might be something else falling onto a neutron star or so, but that's me now a bit wobbly and slightly guessing. Sorry, I'd need to look it up. So they're related in the sense, yes, they're gamma rays and then they're bursts, but it's not cataclysmic.
Okay, thank you. I don't know whether John has anything extra to add to that, or is that?
Yeah, if you can hear me, the only thing I'd say is that some fast radio bursts repeat, but there's also another whole lot of them that are only ever seen once. So there appear to be two populations of fast radio bursts as well, just to add to the confusion.
Yeah. Do you, the fast radio burst, it sounds like they're short as well. Do you know how long they are?
Few milliseconds and with very fast variation.
Okay, so I would guess there's something very different for the following reason. So with gamma ray bursts, as you go to longer wavelengths, the time scales automatically get longer from the way the explosion works. So the gamma rays are milliseconds or seconds. Optical, as I already said, might be minutes. By the time you're in radio waves, it's about a month or two that we're talking about. Okay, so my feeling is
yes.
It will be different, but I would have to look it up. It's a good question, which I don't know the answer to.
Okay, thanks very much.
Yeah.
Okay, so just a couple of more questions if we've got time. Ramsey has asked, are gamma ray bursts similar to pulsars? What's the kind of connection?
Okay, yes, so that I can answer. So a neutron star that rotates and emits a pulse, a radio pulse along its axis, that's a pulsar. Okay, and those just in a way can live forever. The neutron star, or nearly forever. The neutron star just rotates merrily away and then pulses away and gives us these pulses. Nothing gets destroyed in the process. Okay, the neutron star just sits there and pulses away. So the relation would be just that they are neutron stars, but it's not that you collide neutron stars or black holes or anything.
Okay, thank you. And Sean's question is, if gamma ray bursts are common across the universe, could the data from their energy and distance tell us about how the universe is expanding?
That is an excellent question, and the answer is yes. So, obviously, I've presented gamma ray burst as sort of a gamma ray bursts as a puzzle to be solved, and then explanations. But then once you're in a way done with it, they're explained, there are plenty of them, you can use them as a tool if they are well understood. And that's where the question goes, right? As you say, we know gamma ray bursts exist, we know how bright they are, we now know what they are, so we can use them because they are so bright and so far away. Exactly, we can measure, I don't know about the expansion of the universe itself, because so that's related to the galaxies, right? So you need gamma ray bursts linked to galaxies in some way, so there is a link there. But the light that comes from the gamma ray bursts to us tells us a lot as it goes on the way, right? It will absorb. And there was a time where the faintest gamma ray burst which we could see, we knew that they had to be further away than the most distant quasars which we could see. We just didn't know how far they actually were. Okay, so that was the case. The other thing is the following. So it's another more fundamental physics.
Hello.
Hello. Fundamental physics point. So as the gamma ray burst explodes, it will emit neutrinos, it will emit light, and it will emit gravitational waves. Those are all different channels. That's what I meant with, should have said so, with multi-messenger astronomy. Okay, that's the different parts. Now, in the one case where we had the merger and we saw also the light, right, coming from it, I'm trying to remember, I think the difference in time was a few seconds, 1 second, 2 seconds, 3 seconds, something along those lines. And we're talking a billion light years distance, which means a billion years. And so on the fundamental physics level, that tells us that the maximum speed for, say, light is nearly up to 1 second in a billion years, the same maximum speed as the gravitational waves, right? And so that's put a very strong restriction, another one on, how well general relativity works. But that's part of the question. How can we now use gamma ray bursts as a tool, right? To investigate distant galaxies and the universe as a whole. Excellent question, yes.
Thank you.
I think we could go on questioning you all night, actually.
I'm happy to answer. There's loads of interesting things.
Anything
yes.
interesting on YouTube, Will? Yep. Maybe.
I just start with one question here from Stephen Schreier. How much mass is discharged in a jet?
That's an excellent question. It has a lot of many layers, and so that's why I'm hesitating. So you know how I said the two neutron stars merge, you have a black hole, you have a disk, you have a jet with magnetic fields, and you have neutrinos. Now it is important that there be little mass in the jet. Magnetic fields don't have mass, neutrinos don't have mass. That's important because this jet has to be very fast, very relativistic when it points at us. The higher the speed, the brighter it will look to us. It's exactly the same effect as the black hole picture, this one, that one, right? These bits are bright because they are half the speed of light or something pointing towards us. Okay, so these jets, there is little mass, and so little mass means, as compared to one solar mass, I don't know, 1,000th or 1/10,000th of it, because you have to put all the energy into the speed, into the brightness. That's, yeah, an excellent question.
Well, thank you very much for that. Thank you for being very patient with us for all this.
No,
can we
my
thank
pleasure.
you again for that? It's fantastic.
Thank you very much.
The talk will be on our YouTube channel afterwards. I think I might need to go and watch it again just to catch up with all the stuff that was in that, but that's great. So next we're going to have The Sky in March from Alan Pickup. Please stay for that as well. Find out what's in our night sky over the coming month.
Right then, bear with me a second. Okay, The Sky in March 2022. Hello, everyone. We had a brilliant talk about the sun by Lynn Smith of the British Astronomical Association on February the 18th. And since March is not going to be a very good month for planets, but a good month for stars, I thought I'd start with the closest star, again, the sun. This is an image of the sun taken on February the 15th. It's a UV image, imaged in ultraviolet by the Solar Orbiter spacecraft, and it shows what is said to be the largest solar prominence ever to be observed, or imaged anyway. As you can see, it's hanging about as high above the sun as the sun is wide. It erupted from a sunspot group on the sun's far side on February the 15th, and it produced a coronal mass ejection, which blasted material outwards into the solar system, but on that occasion, away from the Earth. There is a video produced from the Stereo A mission showing the blast emerging from the occulting disk in the middle of this image. Let me turn the pointer on. Laser pointer. There we are. There's the blast going away from the sun. Now, there were other images obtained of this same event. This is a camera on the SOHO, the Solar and Heliospheric Observatory, which is located at the L1, Lagrange 1 position, which is 1.5 million kilometers closer to the sun than the Earth. If you look at the image, look at the movie closely, you'll see lots of speckles and dashes and so on there's noise on the detector caused by energetic particles. But there are a couple of other things to spot besides the emerging coronal mass ejection. And they're in this lower part of the image. If I zoom in on that, can you see these two objects going in convoy in towards the sun? I'll lay it on one more time. Well, they're comets. They're plunging to destruction in the sun. They're Kreutz sun-grazer comets, fragments of a giant comet that disintegrated many centuries ago. And we now know that we know of around 4,000 of these Kreutz sun-grazers. Now there have been several. Excuse me a second. There have been several solar flares and coronal mass ejections over recent weeks, and these can cause aurorae and geomagnetic storms on the Earth. In fact, there was a geomagnetic storm on February the 4th, just a day after SpaceX launched 49 new Starlink satellites. Now, those satellites went into low Earth orbit, and that's deliberate. They check them out in low Earth orbit, and only if they're properly working do they then boost them up to increased heights. Can I just, I've got a slight problem on the display here. Let me just turn off the laser and, right, much better.
Right. Those satellites went to low Earth orbit and were to be checked out before they could be boosted to the higher orbit, the normal operational orbit. The Earth's atmosphere was heated by this geomagnetic storm, and that causes the atmosphere, the Earth's atmosphere, the outer atmosphere to expand outwards, so it increases the density at the satellite heights, so that the satellites experience more drag. Now, SpaceX had tried to protect the satellites by putting them edge on to their motion, but it wasn't enough to let them survive, and all but 11 of those 49 new Starlink satellites spiraled down to their destruction and burnt up in the atmosphere. Sad. Not to worry, though, SpaceX has had 3 more launches since then, since the 4th of February, or the 3rd of February when they launched that batch. They've had 3 more launches since then, carrying another 143 Starlink satellites into orbit, and all of them without mishap so far, including another 47 of the blighters yesterday. Now, I think Lynn also mentioned sunspot number when she talked to us. This is a diagram that appeared earlier this week on spaceweather.com. Shows the level of solar activity since 1975. Now, the green lines on here show the daily measure of sunspot number, which is an index of solar activity, index of sunspots, which is roughly 10 times the number of groups of spots plus the number of individual spots. The black line is the monthly average, and we're about here at the end of the green area. It's clear that the sun's activity varies in this approximately 11-year sunspot cycle, and that also successive sunspot cycles are not all as intense as each other. Astronomers have great fun trying to predict what the next cycle of sunspots will look like. Will it be a powerful cycle with lots of sunspots, or will it be a weak one? The expert panel thought that the next cycle, which is number 25 in the series of, since they started counting them, will be similar to the cycle 24. So they thought that the prediction, the blue line on this chart, will be similar to the average of the last cycle. However, a new theory by 2 US solar physicists, McIntosh and Lehman, links the height of the coming cycle to the delay in completing the cycle before. And on their basis, they predict that the new cycle will be average or rather stronger than the previous cycle. And that's what they show in this orange, this taller graph here. And you can see that the sunspot numbers are taking off apparently above the level that was previously predicted. And not only is it not going to peak as they thought in 1924, or about 24, 25, it'll peak a little bit earlier than that. So we'll need to wait and see. Anyway, what's the sun doing this month? Well, that's the ephemeris for the sun for the month of March. And if you look at the times, the sunrise, sunset times, or the nautical twilight times, which correspond to the times when it's effectively dark in the evening and the morning, then you'll notice that we lose more than an hour of effective darkness in the evening and a similar amount before dawn. So the nights are getting longer by more than a couple of hours during the month. The vernal equinox, of course, occurs when the sun crosses northwards over the celestial equator. The vernal or the spring equinox occurs on March the 20th. So that's when days and nights are roughly equal around the world. And of course, we in Britain enjoy the start of British summertime by getting up at 1 o'clock in the morning on March 27th to set our clocks forward by an hour. The moon during the month of March has these phases. We are just after new moon. So the new moon was on Wednesday, and we'll see it emerging in the western sky over the next few nights with quite strong earthshine. It's a diagram I often shows a 360 degrees around the equatorial region of the sky, unwound across the screen. And the sun is just about to cross over from one side of the chart to the other. Those arrows illustrate its motion from Aquarius to Pisces during the course of March. The only obvious planet in the sky this month is Venus, and even that's very low down. That's its relative sizes and phases on 1st of March and the 1st of April. But it's very low down in the southeast before dawn, at least from our latitudes. If you're further south, and certainly in the southern hemisphere, then you get a much better view of planets in the morning sky. Mars is currently below Venus, much fainter, much smaller, much more boring to look at through a telescope just now. Mercury and Jupiter are both definitely lost in the morning twilight, while Saturn is just emerging from the twilight at the month's end. It's getting close to Venus in the sky by the end of March. This is an all-sky diagram showing the north and south views of the sky, showing again now as white stars on a black background, the negative of what I usually show. And I always pick out the plough, and you can see the plough climbing quite high into the east at these times. And opposite the plough, the other side of the pole star, is Cassiopeia. In the south, we've got Leo, and Orion is down here, sinking into the western sky. And to the right of Orion, we have the Pleiades and Aldebaran and the Hyades in Taurus. Now, I'm going to break the habit of a lifetime by starting with the morning sky just before dawn. This is the view 1 hour before sunrise tomorrow morning, as seen from Edinburgh, looking towards the east. And that's about the only time we have this month in the morning sky of spotting any naked eye planets. As for most of these charts, overhead is towards the top of the diagram. You can see southeast or northeast and east. The cardinal points east are illustrated along the bottom. And the black line, the black curving line area at the bottom is the Earth. So that's the horizon as we face east. If you look in the morning sky, you can see the summer triangle, Vega, Deneb, and Altair. So the summer triangle is coming into view in the morning. The summer can't be far away, can it? Venus is obvious, but it's down here, very low down in the southeast, only 5 degrees high an hour before sunrise, magnitude minus 4.5, and 41% sunlit tomorrow, 30 arc seconds in diameter. And there's the little snapshot I showed earlier of its changing appearance during the month. Mars is, as you'll see, below Venus. And there's the relative size of Mars and its magnitude 1.2, which compared with a magnitude minus 4.5 to minus 4.3 of Venus means Mars is about 1/200th as bright as Mars. And since it's lower and nearer the horizon in the twilight, you'll be hard pressed to see it. It does get higher over the following few minutes later as the sun gets higher too, below the horizon. So it is possible to see Mars, I think, with binoculars, but it's not very impressive. Certainly not worth following up with a telescope. This is the view on March the 27th, again 1 hour before sunrise. The same direction, looking east, but this time I've made the Earth transparent, and the horizon is that green line. Everything below that line is below the horizon. And you can see that even just 1 hour before sunrise on March 27th, Venus is very low indeed. In fact, it's 1.7 degrees high as seen from Edinburgh. And Mars is now towards the right of Venus, and it's only it's just sitting on the horizon, 0.4 degrees above the horizon, less than the moon's breadth above the horizon. And Saturn is down here just below the horizon, at magnitude 0.8. So it's brighter than Mars, and it might become visible in binoculars by the end of the month. if you wait as the morning twilight brightens. The moon is also visible. The moon is also in the sky, or just below the southeastern horizon and visible before dawn. But here's a warning: a lot of magazines, articles you might read this month say that these planets are spectacular before dawn, easily seen before dawn. They even claim you can see the moon when it passes below Venus and Mars. But that's certainly not the case for our latitude. It's just fake news. From the morning sky to the evening sky, this is the view looking to the west in the early evening. Again, it's 19:30. In fact, tomorrow night, 19:30 is already gone tonight. So this is 19:30, 7:30 p.m. GMT tomorrow night, looking west from Edinburgh. You can see the Milky Way arching over the sky, and you can see, you may be able to see at that time, a very thin sliver of the moon, 15 degrees high, in fact, in the western sky. But this glow, I want to draw your attention to, that is the zodiacal light. A good time of the year now for seeing the zodiacal light. It's a dim glow. I've increased its appearance on this stellarium view to make it more obvious. It's a sort of cone of light that reaches up from the sun, which is below the horizon down here. And it's held to be dust in the solar system, in the plane of the planets, perhaps meteoroids from comets or collisions between asteroids. Though data from the Juno mission, which when it was on its way to Jupiter, suggests that the dust close to the Earth, at least, is most likely to have come from Mars. Now, the moon is 11% sunlit tomorrow, so it'll be quite spectacular with bright Earth shine, the full Earth in the lunar sky. On the 6th, it's 18% sunlit. On the 7th, it's 26% sunlit. On the 8th, next Tuesday, it'll just be roughly where my laser pointer is, near the Pleiades, 4 degrees below and left of the Pleiades and 35% illuminated. Now, usually when I give these talks, I pick a time late in the evening or mid-evening to look around the sky, and let's start in the north. At this time, 22 hours GMT on March the 16th, which corresponds to 22 hours BST or 21 hours GMT at the end of the month, and at these other times as well. Polaris, as it always is, in the middle of our northern sky. The Plough are very high in the east. Vega and Deneb, the top 2 stars of the summer triangle, we saw them in the morning sky at that time of the evening. They're about 11 degrees. Both of them are about 11 degrees high between the north and the northeast, but they're climbing and getting higher. And the Milky Way is starting on the northern horizon, going through Cygnus and climbing up through Cassiopeia into Perseus. Turn west at the same time. The 2 brightest stars in that part of the sky are Sirius and Canis Major in the southwest, quite low in the southwest, but now to the left of Orion, whose belt is now parallel to the horizon and pointing to the right towards Aldebaran and the Pleiades. Gemini is above Orion, and as it does when the Gemini is in the western half of the sky, Castor lies to the right of Pollux. Now, when they're climbing in the eastern part of the sky, Castor always lies above Pollux. Pollux of the 2 is the brighter star. But that's the view at 10 p.m. Tomorrow evening. As it gets dark tomorrow evening, in fact, Castor and Pollux and Gemini are more or less very high in the south. Orion is much more obvious in the east, in the southwest rather, and Sirius is low down in the south. So we've still got plenty of time to view the delights of Orion and the Orion Nebula, of course, which lies in the sword of Orion, which hangs below Orion's belt. I'll pick a region of interest now, and I'm going to zoom in on this area because there are a few things I want to pick out. Here it is with some of the brighter, messier objects identified, including some open clusters up here. You've got M36, M37, and M38 in Auriga, and M35 in Gemini, in the feet of Gemini. All those are quite easy to spot through binoculars. And M35 in Gemini is the brighter of them all. I showed images by ASE photographers of all these last time I spoke in January, so I'll not repeat that now. I also showed M31, the Andromeda Galaxy, which is getting a bit lower now in the western sky, or to the sky to the north of west. It's about 20 degrees below Cassiopeia in the sky at this time of night. Another open cluster with a Messier number is M34. Here it is in Perseus, and there's an image taken by William Bonner of the ASE taken on Christmas Day. I admire his perseverance. That's 5 degrees away from the famous eclipsing binary star Algol in Perseus, and the cluster, this cluster of stars, lies 1,500 light years away. It's about a third as far away as those clusters in Gemini and Auriga. And it's about 200, the stars in it formed around 200 million years ago. So their stars there are intermediate in age between those of the Pleiades and the Hyades. A couple of brighter star clusters lie here between Cassiopeia and Perseus. We call them the double cluster, or H and Chi Persei. There's an image by Mark Phillips of these two star clusters. The left one is also called NGC 884, or Chi, that's Chi Persei. And the right-hand one is NGC 869. The surprising thing, both of them are around 7,500 light years away, and the stars in them are only around 14 billion years old. There are lots of young stars in those two clusters. Surprising thing about them, of course, is that it wasn't catalogued by Messier, rather. But it's been recognized, in fact, since the time of the Greek astronomer Hipparchus, as early as 130 BC, 130 BC. The same area of sky, we have a comet. Might be the brightest comet next month, but it's this month, but it's not very spectacular. Here is its path from the beginning of March the 1st to the middle of April. You need a telescope to catch it, to image it, to glimpse it. It's currently around magnitude 10, around down here in Aries, but it's going to be fading by more than a magnitude during the course of March as it climbs up towards Auriga. But we do have two images taken, both of them on February the 26th by Peter Black and Mark Phillips of this comet. So I thought I'd show them to you there. And I'm pleased to see that we've got more people in the society interested in observing comets and also working out their brightnesses and reporting them. This is the view looking south at 22 hours GMT on the mid-month. We have the moon in Leo by that time. Here's Orion and Sirius. Castor and Pollux higher in the sky. Overhead, as I say, is around here. And Leo is here. The region of interest I want to focus on just initially is the constellation of Gemini, because there is a second comet here, comet 2019 L3 Atlas. It's tickling the feet of Castor and Pollux as it's moving in this direction during the course of the next 6 weeks or so. Positions, as on the previous diagram, the positions are marked every 5 days. I mentioned it in my January talk, and I showed this image by Mark Phillips, taken on January the 3rd. It's also around magnitude 10 at present, but it is expected to fade slowly. The comet isn't periodic, and it's now on its way out of the solar system, following perihelion beyond the orbit of Mars, and in fact, beyond the orbit of most of the asteroids, perihelion on January the 9th. I'll pick a second region of interest on this looking south map, and that's this one. It takes in Gemini, but stretches across to Leo. And this is it in close-up. And again, with this one, I'm showing the Messier, the brighter Messier objects. The right in the middle, and pretty well in the middle of Cancer, this is constellation of Cancer, the rather dim constellation of Cancer, is M44, Messier 44, or the Beehive, or the Praesepe star cluster. Naked eye in good conditions, and very easy to spot through binoculars. And of course, it's between Castor and Pollux and Regulus. You've just put your binoculars across this region. You can't miss it. Pat Devine obtained this image of Praesepe, or the Beehive, on February the 6th. And I mentioned last time, there's another open cluster in Cancer to the south of M44, which is M67. And this was an image I showed in January by Nigel Goodman. Towards the right of the chart, and close to the border between Canis Minor and Gemini, there's an interesting object called the Medusa Nebula, catalogued as Able 21 by the University of California astronomer George Able, who discovered it only in 1955. Now, Ian Smith obtained an image of that on January the 24th, and that's his image. Able called it a planetary nebula, but for a long time after that, other people didn't believe him and classed it as a supernova remnant. So instead of being a planetary nebula like the Ring Nebula in Lyra, it was a supernova remnant like the Crab Nebula in Taurus. But in fact, now it's widely recognized as being definitely a planetary nebula. It's around 1,500 light years away and 4 light years across. And the UV radiation from the central star in the nebula about there is energizing the material that lies around it. That material was thrown off from the star when it reached the end of its life as a sun-like star. I don't know when that happened, but probably thousands of years ago, probably thousands of years ago. Right, now, let's turn our attention towards Leo, and what Leo lacks in star clusters, it more than makes up for in galaxies. And there are even more than the 5 that are shown as red ovals on the diagram in the south of the Leo. Some of them are, 3 of them are in the Leo triplet, which lies near Leo's hindquarters. And there's an image by Ian Smith of the Leo triplet. There's been other nice recent images by Pat Devine, Hugh Somerville, William Bonner, Nigel Goodman. And sadly, I can't show them all. I'll just stick with the one from Ian at the moment. And if I put labels on the 3 galaxies you can see there, they lie, those galaxies, between 30 and 35 million light years away. And they're all spiral galaxies. You can clearly see 2 of them as spirals. This one, the spiral galaxy, is seen edge on. That's NGC 3628. So the dust in the spiral arms are cutting right across it, and it splits it in 2. A more popular name for that galaxy is the Hamburger. But it's also known sometimes as Saura's galaxy, or Sarah's galaxy. No one is certain why, but it's thought it may be in homage to the English poet Sarah Williams, who lived in the 1800s and wrote a famous poem called The Old Astronomer. And I'll show 2 lines from that poem. There they are. And these are lines that some astronomers have engraved on their tombstones. Though my soul may set in darkness, it will rise in perfect light. I have loved the stars too truly to be fearful of the night. So that's penned by Sarah Williams in the 1800s. Now, I've been looking at this area. There's another group of galaxies, the M96 group here. Our astrophotographers have not been so active on this one, and I've had to resort to a WikiSky image of the galaxies in that. Perhaps we can find, there's plenty of time before Leo disappears to obtain more images of those galaxies. Now, I've been spending some time talking about Leo, and that's of course in the direction opposite to the sun. So it's in the direction of the Lagrange point 2, the L2 point. And as you all know, the James Webb Space Telescope is circling the Lagrange point 2. So where is it? Well, this is where the Lagrange point 2 is as I speak at this time tonight. Yeah, pretty well exactly. And so you might expect the James Webb Space Telescope to be somewhere around here. But if you remember how the James Webb Space Telescope was deployed, it went into an orbit that circles the L2 position. Actually, it's quite a wide orbit, as you can see here. This was it launching from the Earth, and eventually it burnt fuel to enter this quite large orbit around the L2 position. So where is it tonight? It's there, right in the middle of the diagram. Just a few degrees to the east, to the left of the Prasepe or Beehive cluster in Cancer. And at the moment, it's tracking up in this direction, more or less northwards and eastwards from where it is tonight. Excuse me. Looking east at our mid-evening times or 22 hours GMT times on March the 16th, that's the view we get. Here's the plow high in the east, the handle of the plow curving down towards Arcturus. If you remember the story, arc to Arcturus and spike to Spica. Well, the star Spica, the brightest star in Virgo, is just about where the sun, at this time, just about where the planet Venus is before dawn. And so I'm going to concentrate just now on Ursa Major, this region, and there it is. Our usual UK name for this is the plow. But it's also referred to historically as Charles's Wain or wagon. And there is a European tradition, in fact, of it being called a wagon. In the US, it's known as the Big Dipper, and it's also known as the Dipper in Chinese culture and several other Eastern cultures. Another common name you'll see is a saucepan with the handle of the saucepan or the handle of the plow and the bowl there. The joining star between the two is the fainter star of the seven that make up the plow, Megares. You all know that the pointer stars, the two end stars of the bowl, point the way to Polaris if you extend them in one direction, and they point the way to Leo in the other direction. And I've already mentioned that the handle can be extended towards the star Arcturus. I'll just mention one interesting star on the plow, and that's the second star of the handle, Mizar, and this was an image taken by Mark Phillips of Mizar and its companion Alcor, which you can see with the naked eye as two stars, very obvious in binoculars. And Mizar, in fact, consists of two stars. Alcor is 12 arc minutes away from Mizar, so the moon would fit more or less side to side across this photograph. Alcor, you can see if your eyesight's any good at all. Mizar, to see it as double, they're only 14 arc seconds apart, so you'll need a telescope to see those as two stars. And you can see it is two because you've got two sets of diffraction spikes from in Mizar here. The two stars here take thousands of years to circle each other. In fact, each of those two stars is a spectroscopic binary star. So the stars are, and all the stars here are 83 light years away. Oh, Alcor also has a companion. Alcor has a faint red dwarf companion, only 1 arc second away from it, and it was only discovered back in 2009, so it's a fairly recent discovery. This is Ursa Major, but this time again, I've turned on the Messier numbers to highlight where you can find, in most cases, distant galaxies. 4 Messier objects to the left-hand side of the diagram have alternative names, which you may recognize: the Pinwheel, the Whirlpool, the Sunflower Galaxy, and the Croc's Eye or the Cat's Eye Galaxy lower down. In fact, all these galaxies down here are not in Ursa Major. They're in Canis Venatici, which is the hunting dogs. It's Latin for hunting dogs, but it's thought that they're supposed to represent the dogs of Boötes, who was not a hunter but a herdsman, So the kind of advantage really should be the sheepdog, perhaps. Anyway, our astrophotographers have got lots of very good images of these galaxies, and I encourage you to look at them on our website or the Flickr pages. And I'll resist the temptation to show them here because we're getting a bit late along on time. Instead, I want to highlight this region, and there it is. If we take a line across the bowl of the plough and extend it more or less the same distance, we get to two other galaxies, M82 and M81. Here's an image by Pat Devine showing the two. Both of them are visible through binoculars. They're about 0.6 of a degree apart, so you could just fit the full moon between them in the sky. M82, this one on the left-hand side is 12 million light years away, magnitude 8.4, and it's visible, as I say, in binoculars, nearly edge-on spiral, but it's undergoing starburst activity. So you can see reddish plumes of material triggered by young stars being born and eventually bursting, expiring as supernovae, probably because of the interaction with the neighbor M81. Lots of supernova debris spilling outwards. M81 is also called Bode's galaxy. In fact, both galaxies were discovered by the German observer Johann Bode in 1774. Also 12 million light years away. And if you look carefully, you can see in the spiral arms pink regions, which are star-forming regions, a bit like the Orion Nebula. There is one other object in this area which I'll pick out, and it's here. It's called HD 84406. It's a star, magnitude 6.4, 259 light years away, spectral type G8, making its surface 870 degrees cooler than our sun. It's the first star to be observed by the James Webb Space Telescope. Just a month ago, on February the 4th, it got its first light on this star. And it'll be studying it for at least the next 3 months to focus the telescope, make sure it's all working, all its mirrors are properly aligned. So the mirrors will each be tipped, each of the 18 mirror segments and the secondary will be adjusted so they all focus that star's light into exactly the same point. The star had to be isolated, it had to be in a part of the sky which was away from the sun, had a reasonable emission in the near infrared so that Webb's near infrared camera, NIRCam, can see it well, and it's proving to be a successful choice. Meantime, Webb is shielded now from the sun because of its large sunshade and cooling to its operating temperature of 40 degrees absolute or minus 233 degrees Celsius. I think the shielded side, I checked this morning, it's only a couple of degrees above its target temperature. And the side of the telescope that faces the sun, on the other hand, is at 27 degrees Celsius, 300 degrees K. This is an image, a selfie, if you like, of the primary mirror taken by JWST, uses a special lens in NIRCam, which was designed to image the primary. The first light image is this one. This is showing the 18 images of that star taken by NIRCam at first light. The two wings are identified. They're the images from the 3 mirrors on each side of the main block of mirrors that had to be swung into position. As you can see, not all the mirrors are lined up in the same place. The next job was to align them up, and this is showing a little animation showing that the alignment of the mirrors and the focusing of the mirrors, and then everything had to be, all the mirrors' lights had to be brought together, complete the image stacking. But even at this stage, the telescope is still working as 18 small telescopes. It's not working as a single telescope, all in phase. Now the mirrors have to be lined up to better than the wavelength of light, starting with what's called coarse phasing, which is going on now when 20 separate pairings of mirrors are used to correct tiny differences in the heights and the tilts of all the mirrors. So the combined star image becomes sharper and more focused, and actual science observations can then begin in the summer. And that's my talk for tonight. Thanks.
Thank you, Alan. I think it's hard to collimate my telescope and focus it as well, but that's even harder. That's it for tonight. Just a reminder that our next talk is on the 18th of March, and that will be on Zoom and YouTube, about HF meteor trail reflections from Anchorage. We have the Imaging and Observing Group on the 9th of March, next Wednesday, for ASC members. So thank you for coming tonight, and see you all again soon.